new graduate students. Probably this is the first time for you guys to come to our seminar series. Each week, most of the time, we invite a speaker and to give us a talk, and that is for the entire year. And we ask the first year student to come here to listen to our talk. And today we are going to have our first talk in this semester and in the same year, in the first year. That is Dr. Shima Parsa, and she is, as you guys, most of you guys, and the newest faculty member in our school, and she is currently assistant professor in the School of Physics. Probably you guys have already had lunch together with Dr. Shima Parsa, and she finished BS and MS degree in Iran and the PhD degree in Wesleyan University. And after that, she spent 5 years in Harvard University as a postdoc. So probably if you guys want to know how hard Harvard students work, you could ask her, and she could tell you should work harder. And Dr. Shama's research is closely related to our imaging science, though she's in physics. She works her current research is in somehow the 3D visualization thing and for turbulence, and later on something like oil recovery. Yeah, sorry, and something she probably Dr. Shima Parsa will mention, but I want to emphasize here: if Dr. Parsa is going to have some new PhD students. So for those of you guys who want to work on physics things and somehow the interaction area with the imaging science, you could probably listen to the talk more carefully and know what Dr. Parsa is working on. So you probably could have a mutual interest. But I will leave that to Dr. Shima Parsa to introduce more. Okay, let's welcome Dr. Parsa to give us a talk.
Thanks for the introduction. So as Dr. Liu said that I'm an assistant professor in physics, and I started just this fall. The work I'm presenting is the work I did as a postdoc at Harvard with David Bates, and he's also a physicist, so this work was all physics. The work was on polymer enhanced oil recovery, and it was funded by different agencies, including oil companies, NSF, and then recently by the Chinese University of Petroleum. So why do we care about oil? Well, we all know that we're trying to use renewable resources, but we still heavily rely on fossil fuels for energy production. So this is the data for last year. This was published in April of this year. If you look at the chart based on what resources we have used to produce energy, you see almost 75% is still oil and gas. So to use petroleum in the recent future to sustain our daily lives. And to produce oil and gas, we have to first recover it. So how did oil come to existence? So this is, this time zero is before the dinosaurs started roaming the earth. There were microorganisms, and going forward now. The microorganisms, as they died, they sedimented on the bottom of the ocean, and then more layers of sand and soil and mud on top of it. And then years passed, and then these dead organisms are now in an environment that is not a lot of oxygen, and they are decomposing, and they are turning into hydrocarbons. And then more sedimentary rock on top of it. The pressure is too high now, and we have a layer of permeable rock. In the pores of this rock, there are hydrocarbons called kerogen, that these are very large molecules that have a lot of carbons, and they're stuck here. Under the pressure in the sedimentary rock, after a few 100 million years, the carbon bonds in the kerogen starts breaking, and then we have hydrocarbons that are slightly larger than the kerogen, Now they need a little larger volume. They start creating these nanometer sized pores, and then they all get together in the slightly larger pores, and this is where the oil is. So at the beginning of the talk, I want to tell you about two kinds of reservoirs, and then I'm going to focus on one kind of reservoir and one kind of recovery. So we have two kinds of reservoirs, conventional and unconventional. The conventional reservoirs are the reservoirs that we have seen a lot in movies. This is a pump, and there's one well, and we recover oil. So this kind of reservoirs are the reservoirs where oil is in the micron-sized pores, and we can access that. The unconventional reservoirs are the reservoirs that we are too impatient to wait 6 million years for the oil to migrate from the nanometer-sized pores to get to the micron-sized pores. So we go with a bunch of trucks and a lot of water, and then we frack the rock. This is hydraulic fracturing. This is a method that allows us to create pores close to the nanometer size pores, and now we have these cracks, and then there is an imbalance between the pressure. Oil rushes into these pores, and then it comes out. And after the operation is done, this declines very fast after a few years, and then they pack up and go frack somewhere else. These reservoirs, they have been around for a while, this kind of recovery, and they're still recovering from that. A very, very tiny amount, but these pumps are going up and down. It's really ironic. All these pictures I Googled, and they're all so beautiful, and there is a sun in the background. And these are the places that we have a lot of contamination. We cannot clean up, so these pumps just go up and down for decades. But the industry managed to just publish the beautiful picture. So we're going to work on conventional recovery, and enhanced oil recovery is increasing the recovery from a conventional reservoir. So how do we do recovery in a reservoir? This is a reservoir. This is the surface of the earth. This is where we are. And the geologists and people who do remote sensing find this reservoir, and they tell us that there's a reservoir there and we can do recovery. What do we have here? On the surface, we have a layer of porous rock, and then we have more rocks and water. Then we get to a layer of impermeable cap rock. So this cap rock has very, very tiny pores. That's why oil and gas cannot get above. So they're stuck here, and we have the reservoir rock right beneath the cap rock. Now what we're going to do is we're going to drill a hole, a well, and get oil out. So in the movie There Will Be Blood, you saw that oil was gushing out. This does not happen anymore. So in the past, there were reservoirs that the pressure was very high, they were very close to the surface, and we would get that. Now we don't get that anymore. Now we have to drill an injection and a production well. At the beginning well, we drill the injection well because the pressure in the reservoir is higher than the pressure in the well. Some oil starts migrating towards the well. But as soon as the pressure between these 2 points are balanced, there is no more production. What we do is we get a pump and start pumping a fluid that's cheaper than oil, to let oil come out. So water is usually the fluid to go. We pump water goes to the pores of the reservoir rock, and then it starts pushing the oil out towards the production. So in the first step of recovery, we use enough water to go from one side to the other side, and we see oil coming out of the production well. And this recovery usually gets 30%. In good reservoirs can do 50%. But they stop this recovery after some time. So we keep pumping water, and then at the end we just have water. Why? Because reservoir is not a big pool of oil, it's a rock. So water has to go through the rocks and then pushes oil out and come out of the other side. But when water finds a continuous path from injection to production, it does not want to explore any other path because the resistance is high. So it just goes through and then comes out of the production. This is where the production levels off, and there is not much oil coming out. The reason for why we don't get all of the oil pushed out by water is mainly attributed to viscous fingering. So viscous fingering is a very fancy word for saying that we have a viscous fluid and a less viscous fluid, oil and water is trying to push oil out. And when water is at the interface is trying to push, the interface of the two fluids becomes unstable, and then one finger of water starts protruding and then goes all the way. So this image is just oil and water between two glass slides. This happens in porous rocks. So this is an example of a very, very synthetic porous rock. We have a bunch of glass beads between two glass slides. And then from the center is filled with oil. From the center, we are injecting a water that is fluorescent, and then we image that. So even when we have this heterogeneous, semi-heterogeneous medium, these fingers protrude, and we have some of them getting there faster, and as soon as one of these get to the edge, there's no production. It just flows through. So to stop that from happening, almost 7 decades ago, people came up with the idea, let's increase the viscosity of water. To increase the viscosity of water, they decided to add polymer to water, because when you add polymer to water, the viscosity increases. Maybe we can suppress the viscous fingering. And that's how polymer flooding came to existence. So after the initial recovery, when we have injected enough water and then it came out of the other side, we're going to start injecting polymer. But we cannot inject a lot of polymer because polymers are expensive. And the polymers we inject are usually synthetic. Synthetic polymers are made out of oil. So if I inject a large, so we cannot have a large concentration in the volume we're injecting. After we inject some amount of polymer, and then this is usually decided by reservoir engineers based on the pore sizes they know and the volume of the reservoir they estimate, they do less than a pore volume of the reservoir. And a pore volume of the reservoir is the total void volume in the reservoir they expect. So the entire, the sum of all the holes in the reservoir. After that, they stop polymer because it's too expensive. They start pushing the polymer with water. And the idea is that polymer is going to go through. It has a higher viscosity, so it's going to have a stable front, and then it's going to push the oil out. And then we continue with more and more water until in the production, we don't see any more polymer coming out, and it's only water. And the total recovery, this is the additional recovery, this is additional 20%. So considering that how much it takes to find a reservoir, drill a well, and set up all of these things, if you go from 30 to additional 20, we have really enhanced the recovery. But there's a tiny bit of a problem. It doesn't work in all cases. So there has been pilot tests that they got no recovery. There has been pilot tests that they expected to have no recovery and they got recovery. So the problem is that we have the simple picture of viscous fingering, two fluids. One of them is more viscous, the other one is less viscous. But reservoir is extremely heterogeneous. And there are things happening in the reservoir that we cannot just assume that a simple model of two fluids with different viscosities can capture. And we were approached by Total at the beginning of my postdoc with one particular question. They said, we have seen recovery of very viscous oils. So these viscous oils are 2 orders of magnitude more viscous than any polymer solution they could have injected into the reservoir, because they cannot inject something that's very viscous. It costs a lot of money to inject something that's very viscous. And they were like, okay, so we did not expect any recovery. This was for a different purpose, but we saw recovery in a pilot test. Can you do some experiments and tell us something? So it was a physics department, so we looked at the problem and said, okay, so this is the reservoir. The scale of reservoirs are kilometers. Oil companies usually take a core sample out. When they drill a well, they take a core sample out. It's tens of centimeters. And then they do some experiments on the core sample. But what's happening is that this is a microcity of the cross-section of the core sample. Everything is happening at the micron-sized pores. And we're physicists, so we're going to go find a fundamental question. The main methods of imaging a core sample are micro-CT and NMR. So in the micro-CT case, they have a source of X-ray, and they put the sample in front, and then they have a detector, and based on how much the X-ray is being absorbed, they get an image here, and then they rotate the sample, and then they get a full 3D image of the core sample. And this usually takes 40 minutes. In the Metro City we had there, we actually did this experiment. So we put a core sample in there, and this is oil left in the core sample. This is just reconstruction of the oil, and these are different sizes. But this took us 40 minutes, and the sample was 2 millimeters by 2 millimeters by 4 centimeters. So we could not see any dynamic. Well, the total amount of oil left in the medium was important, but we couldn't see any dynamics. And the fastest X-ray data available is from synchrotron by Shell, and they have seen one event. That was a slow event, and it took 16 seconds for oil to be pushed. So this is not an option for something you're exploring. The other method of imaging is NMR. I'm not going to even try to explain this because there are people who know better than me. So in the NMR, in porous media, we usually fill the medium with water, and we measure the relaxation time for the hydrogen. And the data they find is that if the pore is large, the water molecules, they diffuse very fast, and then they have a metric of how large a pore is, and then they can measure what's the distribution of the pore sizes. There is some more recent data using a pulse gradient spin echo magnetic resonance imaging, and they have a layer of glass beads in a petri dish, and they're growing an algae in there, and they're measuring the biomass using this method, and also they are measuring how fast water molecules are diffusing. This is one of the best measurements using NMR to get velocity data in porous media. But it's still, it takes 300 milliseconds, and they get one slice. And this is a group at Montana State, and this is what they have been doing for a long time. It's a very beautiful data, but there's a tiny bit of a problem. Our dynamics is a little faster, and we have a larger sample. So we decided to change the problem. If we cannot see inside a rock, let's make a rock we can see inside of it. So we replaced the rock by model rock. So this model rock, this is a real image, and this is how large it is made of glass beads. So I take a quartz capillary, fill it with glass beads, and then put it in an oven, let it bake. So all the glass beads are stuck to each other. The pores are still there. It doesn't completely melt, but it's solid as a rock, so I cannot break this. So I have a rock now that's made of glass, and probably I can do some imaging. The pore sizes of the rocks depends on how large the glass beads are. So we use 20 to 70 micron glass beads, and we want to do optical imaging. So the trick to do optical imaging is that you need to overcome the refraction of light from so many surfaces. So let's ditch water and oil and get two fluids that have the same indices of refraction as water and oil, and they have the same properties like water and oil, and they do not actually mix with each other. So we got a water phase that is made of dimethyl sulfoxide and water, and this is a glass vial filled with glass beads, and then we poured it on top, and we can still see through. And then we formulated an oil. I like Cargill immersion oil. They give you exactly what index of refraction you need, and they're very nice oils, very inert. So now we have changed the problem. The physics will be the same, and now we need an imaging technique. So the imaging technique we used was confocal microscopy. So confocal microscopes are really great. They have all kinds of lasers in them. You can do a lot of imaging with them, and you can do 3D. This is an image of my apparatus. This is a pump that's pumping fluid, and these are the tubes that are bringing the fluorescent fluids inside. So I'm going to just explain confocal microscopy in a few words. If we have an objective here and we have a sample and we get multiple rays coming, if you put a pinhole, it's going to reject all the rays that are not coming from the focal plane of the objective. So we get a data that is only from this one plane, which means you can do 3D without seeing other planes. And confocal microscopes have some more optics in them. One of the good things is that they have the dichroic mirrors, that they have 2 wavelengths. So you shine light and what at one wavelength, and then it goes to the sample, it emits at a different wavelength that will be emitted, and then it goes to the PMT, and then you collect a lot of that light. Now we have a system and a confocal microscopes that has multiple lasers, so we can actually put dyes in our sample and do imaging. The other thing about confocal microscopes is that they have an automated stage, because microscope usually sees 1 millimeter by 1 millimeter, and this is what you see in one image. So these are glass beads, and around them we have water which has fluorescent dye in it and is white. And then we can use the automated stage to go around and scan the whole medium and get a full image of the few centimeter long sample. Moreover, we can do 3D, so we can use the Z automated stage that it just scans up and it moves the objective up and down. We take one image, and then we take images at different intervals, and then we can reconstruct them in 3D. Now that we have a setup that can do dynamics, and if you remember cameras or PMTs, they can scan at tens of milliseconds, and they can actually see things happening very fast, we can do experiments. One of the most important things to see in porous media that's very valuable but not very accessible is that how water or any fluid, how fast it goes through different pores. So these are a bunch of tracer particles. These are 1 micron fluorescent tracer particles, and these are glass beads that are black and nothing is happening. And they are being pushed by a pump through the porous media, and we can actually go and follow these, do a particle tracking, measure the speed of these tracer particles, and then as long as the tracer particles are small, we can use that speed to tell what's the speed or velocity of water inside those samples. And since everything in oil recovery happens extremely slow, and the rule of thumb for velocity is 1 foot per day, we can flow these things very slowly, and it gives us a very, very laminar flow, so nothing changes as a function of time. So what we can do is take our one image, measure velocity, go to the next step, and then take multiple images, and then stitch them all together, and get a full map of the velocity along the sample. So these are 150 micron glass beads that are black, and then this is the velocity distribution, just a color map, inside the sample. We are injecting at 10 micron per second, and if you see in just a glass bead, which is a very simple modern rock, we have velocities that are around 0, and we have velocities that are 100 micron per second. So this is something that has always been missing from research in porous media, is that we don't have access to what's happening inside. So what we always measure is what's the pressure across one sample and how fast we're flowing it in. And instead of using an average value, we should always remember that this is very, very heterogeneous. And then I'm going to come back to this and tell you why this heterogeneity means when you have a recovery phenomenon. Okay, so we have our system that we can measure velocity inside, and now I'm putting an oil, a model oil that's black and has no fluorescent, and I'm flowing water, pushing oil out, and we're looking at how recovery is happening. So the next step would be see how much oil is left in the medium, and then quantify that. This is very simple when you have a system that's static. After you do a recovery, we can just go and find all the areas where we have oil and do a measurement. To do a polymer flooding, there was a big challenge. So the question I was working on was, first of all, they wanted to use the polymer that's actually used in the field. So we had to use that polymer. And also the question was, can we recover heavy crude oil? And heavy crude oil is very viscous. To use an oil that has such a high viscosity, we searched a lot and we couldn't find any oil, so we decided to do our first measurements with the actual oil and the actual polymer. So the oil we used was from Venezuela, and the polymer we used, and I'm gonna just call it polymer from now on, is partially hydrolyzed polyacrylamide. The molecular weight is 20 megadalton. If you work with polymers, this is extremely large. So a glucose is 180 dalton, so a dalton is around a gram per mole. And this is a very, very large polymer. This is only synthesized for particular application, and that's only for oil recovery. So the viscosity being high, the viscosity of water is 10 to the minus 4 Pascal second. Heavy crude oil, when it's heated for the experiment, and this is actually me trying to pour oil into a sample, is 2.4 Pascal second, and honey is around 10. So this is extremely viscous. And there was some other issues with oil if we wanted to use any other oil than heavy crude oil, was that oil is, other than being very viscous, it has many components that it gives us some elasticity. So I put the oil usually in the oven, heat it up at 65 for a few hours, so I can actually put it in a syringe, and this is the hot oil I'm putting in here. And as I leave it there and I turn the vials backward, it starts flowing, and it feels like honey after a few drops come out. So it's still trying to flow, and then when it has one continuous strand of oil, you see it keeps stretching itself. So when you're working on a physical problem and you're trying to answer an industry question, it's always good to consult industry, because there are things, especially the chemistry of problems, that we cannot reproduce in the lab, and sometimes using their material helps us. So I'm going to go do a recovery experiment with actual oil and their polymer. And I'm going to replicate what they do in labs in Total. So they have in reservoir, they use some amount of water that depends on the reservoir. But in lab, they usually use a recipe. So they say, let's recover a lot of the oil, as much as we can, because the volume of the sample is small. So I'm going to use 15 pour volumes of water to remove as much as oil I can in my first step of the recovery. And then I'm going to start a polymer flooding, which is the enhanced part. So in the polymer flooding, I use 5 pour volumes, and then I continued with something called chase water, which is 12 pour volumes. These numbers matter to the industry, because less pour volumes of polymer is very important. They put less polymer in there, and it's going to be cheaper. There was a little bit of a problem. I'm going to use optical imaging, and I'm going to try to look at crude oil. And crude oil is black, so you cannot see inside this. And when I use microscope to look at this, so these are 2 slices. I put fluorescent dye in water, and then I can find where water is, which is blue. And crude oil has asphaltenes, and asphaltenes just fluoresce at 633 nanometers, and they give us a signal. And I colored them purple. But then there are all these black areas. Some of them are glass beads, they're not fluorescent. And some of them are because oil blocks the light and it doesn't reach the layer above. So we have this challenging part that I colored gray here, which is we don't know if it's oil here or it was because there was oil here, what is in here. So the imaging was very limited. We could do almost 200 micron into the sample, and the sample is 2 millimeters. So it was not working well, but we had to find a way to solve this problem. We decided I'm going to measure whatever oil is coming out of this. So this is 2 millimeter, 2 millimeter, 4 centimeters, and it's filled with glass. The total volume inside this sample is 100 microliter. And if you don't know how much 100 microliter is, this is 100 microliter drop. I used the pipetter to put it there. I have to measure a fraction of this that goes into a tube. So that sounds like a very, very bad problem, because the tubes are much larger than the sample itself. But there's always a solution in imaging. I took everything that was in the tubes. When I do a water flooding, I have one tube. Anything that comes stay in the tube, and then we clamp the tube. After the experiment is done, I just pull all these tubes out and use tetrahydroforan. It smells really bad, you have to work under the hood. And dissolve whatever is in the tube and put it in a bunch of vials. And then use a UV with a spectrometer to measure the absorption of light in these samples. And if you go and do a bunch of measurements, crude oil has an exact value, 405, and the absorption depends on how much oil you have. So I can go make a calibration curve and know exactly how much oil and THF I have, and then use a calibration curve and compare with the data I get, and then I know exactly what's the concentration of oil, and I know how much the volume of THF is, and it's always much larger than the volume of oil. So I can calculate how much oil was in grams in each of these vials. And then combine that with my confocal measurements. So this is now what I've done. I've used the polymer that they gave me, the oil that they gave me, and I imaged the sample at a depth around 100 micron. After the first water flooding, whatever black is, I don't know what it is. If we have blue, it means it's water. If I have purple, it means it's oil. And then I match that with the data that I directly measured the volume. So in the first step, 27% of the oil in the medium was recovered. And then I'm going to flow polymer. After I flow polymer, we see some changes. Some of the blue has been broken up, and some of them have moved. Some of the purple is not there anymore. The data based on what came out was 0% recovery. So this is horrible because polymer flooding didn't do anything. And then I continue the recipe and I go on with chase water. During the chase water, I don't need to explain this. This is much more blue. So there is more water here, and in the data that we got based on what came out, we had an additional 17% recovery. So this is very, very close to the industry because they have like something like 30%, and then in the best case, they have 20%. At a lower concentration because we couldn't flow that, but the total concentration at the end matched, and I got 20%. And we were very happy, but well, they could have done it in total themselves, so they didn't actually need me with my fancy microscope to do that. But we decided, okay, our samples are smaller, we're gonna go explore the entire phase space. What's the phase space? We can change our molecular weight of the polymer, we can change the concentration, we can change the size, the size of the micromodel, we can change the size of the pores by using smaller beads or larger beads, and also we can change the wetting condition. So out of all these, apparently these two, the polymer is the one that actually mattered the most. And we found that among different polymers that was provided by the oil company, only the large molecular weight was important, and we changed the concentration. A fancy way of saying concentration is you go above overlap or below overlap, and it's very simple. Below overlap, the polymers, they don't see each other. At the overlap, they start seeing each other, and then above overlap, you have a lot of polymer. And we found that to get enhanced recovery in the micromodel, you just need the large molecular weight, and you just need to be barely above the overlap concentration. So if you do rheology of polymers, this overlap concentration is defined over a very large range. So being within a few percent means that you're barely any different from the overlap concentration. So overlap was like 200 ppm, and we got at 250 ppm. This is within the margin of error. So just getting to the overlap concentration was important. And this was very important for the oil industry because they use polymer to suppress viscous fingering. So they want to increase the viscosity. To increase the viscosity, you need more polymer. But we told them, we don't think you need more polymer, you just need to be at overlap. And overlap is a very low concentration. And well, I'm hoping that in future tests they actually don't go that high. It's a good news for them because it's very cheap now. And also, pumping is a very big issue. So if they have to pump a very viscous fluid into the reservoir, they have to run their pumps at a higher pressure, and this is not something they actually want to do. Okay, so we have all these numbers, and they said we can do a core measurement and compare that, and they actually did that a few years later. Okay, so in the core measurements, they got some agreement with us. In most of the cases, cores have a much heterogeneous pore size distribution, so they could do better with the intermediate molecular rate. But what is the physics behind all of this recovery? Okay, physics of recovery is very simple. We have one fluid that's stuck there, and we have another fluid to push it out. So I reduce the problem to a tube. I have water with a viscous force pushing oil that's trapped there. So two fluids that are not miscible, there is an interfacial tension between them. And also in the case of crude oil, if you leave crude oil on the surface of the glass, it starts wetting the glass. So there is a contact angle too. All we need here is this viscous force by water is to overcome the capillary force that is at the interface, if we have one tube. And this is true, plus the fact that the viscosities matter. So there are two non-dimensional numbers here. So if I have oil left here in these, between these grains, as soon as the viscous pressure overcomes the capillary pressure, it rushes to and fills the pore. And this is a very quick, so this is one of this is my data from the oil and water, that model oil and water bottle. So this is like 2-3 frames. The frames on this experiment are 35 milliseconds. So you see that this happens immediately. As soon as it overcomes the capillary pressure, it invades the pore and stops there until more pressure is built up and it invades another pore. So all we need to know is we need to know viscosity, what's the velocity of water, what's the properties of the interface, interfacial tension and contact angle. And these are things that we could measure in the lab. On top of that, we need to always think about the viscosity ratio because there is the viscous fingering. So if we have fluid that is more viscous, and this is now water and glycerol trying to push oil out, and it's more viscous, we get a very nice clean interface. It just pushes and goes out. If we have real water that's less viscous than the model oil I used here, it leaves a bunch of oil behind. And this is viscous fingering in porous media. So I have a few parameters to look at. I need to look at the difference between the pressure, the viscosities, and see if we are changing the capillary pressure because we have added this molecule, which is a polymer, to this mix. Does it affect the interfacial tension between the two fluids or not? This has been seen with surfactants. When you want to mix oil and water, you add some mayo to it, and then they will mix. So a surfactant can play a role of decreasing the interfacial tension, and does the polymer play that kind of role? Or the last one would be, are we increasing the viscous pressure? Because viscous pressure is viscosity times velocity of water. And now we have actually a polymer solution. So we go in and look at all these things. I'm going to make it very short. This is where crude oil is. This is where water is, and this is our polymer. So the viscosity difference, 2 orders of magnitude, there is no way I could match the viscosity. So that's out. Let's look at the other components. So the interface is very simple to measure. We can, to measure interfacial tension, there are different ways. One of them is just if you make the largest drop of oil you can in water, and then you make the largest drop of oil you can in a polymer solution. And the size of this only and only depends on the interfacial tension. And well, we actually measured that because you can just fit a circle on this and measure the interfacial tension if you know the density of the two fluids. But from the images, obviously, we were not changing the interfacial tension by adding the polymer. Also, contact angle is very simple to measure. You get a glass slide, the same material as your porous media, and then put a drop of oil and around it is water. And these images are backwards because oil is less dense than water. So I put the glasses back and then I inject a drop from the bottom and then measure that. So it's the same. We cannot put water on oil because oil is black. So the contact angle did not change after I left this drop of oil on the surface of glass around filled with polymer solution for 6 hours. So, so bad news, this one does not work either, but we still have one component to look at. Are we increasing the pressure from water? The pressure from water is viscosity of water times velocity of water. Since in all of the experiments I did, I used a pump. The pump goes at a constant flow rate. So we were not actually increasing the flow rate at all. And to match what was done in reservoir, which is they always work at constant pressure because constant volume is extremely expensive, we had to drop our flow rate because we had a slightly larger viscosity of polymer. Now the multiply of both is the same as what we started with. And then I just proved myself completely wrong because none of these actually worked. But we saw that there was recovery. Well, there was a microscope image and there was actual oil coming out of the micromodel. So something was happening and we missed that in our thinking. Let's go trace the steps of oil. Water flooding, you get recovery. Polymer flooding, no recovery. Chase water, more recovery. Everything I was thinking about was polymer flooding. And that's because I read too many papers, because everybody thinks polymer is doing this. And polymer was not doing anything. I could see that from the beginning. So what's happening? So on all of those papers I read, people have talked about polymer retention and how to suppress that because you don't want your super expensive polymer to go into the rock and stick to the surface of the rock because it's very expensive. But could it actually matter in the experiments I did? Because polymer was not doing anything except just going through. And there was a very simple way to test that. I assumed, let's just assume we just flow polymer to this porous media. So I took my porous media, no oil. And then went back to the first principles. We are flowing something into this, so there's a flow rate, and there's a pressure drop, and this thing has a resistance. So it's just pressure, voltage is equal to resistance times current. That's it. It's the same thing. Well, instead of resistance, they usually call it permeability because resistance is not very positive. And then we can measure that. I can measure the permeability of the medium if I know what the flow rate is. I know what's the pressure drop across it. I know what kind of fluid and what's the viscosity. And if I know the length of the medium and the cross-sectional area. And then I get permeability. And then I can fill the medium with polymer and remeasure that. So I let polymer go in, and then I flush it slowly out with water, and I remeasure the permeability, and it decreased. So polymer was going there and getting stuck. Well, this was known before me, but, well, does it actually matter? Well, if I could see where the polymers go, this is not real, this I just drew it. Because this is a glass bead, and these are giant polymers that are stuck on the surface of this. If I could see them, I could tell what's happening inside the porous medium. But well, I cannot see that. Well, someone told me to use small angle scattering, and maybe you can get some data on this. Well, I haven't done that because apparently we have to go to a national lab to do that. But there are things I can measure. Let's just stick to the optical things I can measure. So I decided to measure the changes in the velocities in the porous media because porous media is very heterogeneous. Maybe there are things I can refer from this. So I put a bunch of tracer particles in the porous media, measured the velocity, and then I started flowing polymer, flushed the polymer out, and I remeasured the velocity. How am I doing that time?
2 minutes.
2 minutes?
2 minutes.
Okay. And then we found that velocities change. Velocities are higher, but it's a little odd. But when you think about the kind of experiment I'm doing, I have this tube, and I'm flowing water at a constant flow rate. And now the tube is smaller because polymer is on the surface. Constant flow rate, we have to maintain the total volume, so it has to go faster. And it, on average, it agrees with the reduction in permeability, but there are things that are important. So this is very heterogeneous. If I had, so this place that was almost zero before is now, there's water going through that. If I had oil here, could it be large enough pressure to push that out? Now I have to actually go and measure that. So we know all of these things. Polymer is retained, permeability is lower, flow has been redirected into different pores, and then can it actually mobilize oil? So we go and use what people usually do is that they say, okay, I have this much length, I know the pressure across this. If I have this much length, I should know the pressure across this. It just scales with the length. And instead of that much length, I picked an oil that was removed. So I took all those images, subtracted them, and then said, okay, so this was removed. What's the length of this? And what's the pressure required to remove that? And it absolutely did not work. Because I scaled everything based on just one tube. But porous media is very heterogeneous. All of the things that you take the bulk and then use an average to see what happens at the smaller scales, they work if you have a perfect crystal. Yes, so all the tubes have the same pressure, they have the same flow rate, but in porous media, it's very heterogeneous, even in a simple bead pack. So if I want to actually answer that question, I have to do a local measurement. I have to find an oil blob and then measure velocity around it and see if polymer actually did something. We have all those components, and it only works if we use a model oil, because now we want to put tracer particles. I cannot say we can use anything bulk like the crude oil measurements. I have to actually use something that I can see through to see the velocity around it. So this is going to be the experiment I'm going to do. I'm going to recover oil by using the model oil and the model fluid, model water, and put tracer particles in water and measure the velocity of water around oil. It turned out to be an extremely time-consuming experiment. So it took me a year to take 2 oil blobs to actually measure it, because the model oil is slightly more viscous than the polymer solution, and if you're not careful and someone touches any of your tubes in the lab over the experiment that takes a whole week, they're gonna mobilize your oil. So I had to tune all the flow rates and hope that no one walks into the confocal room and no one touches anything. And I got 2 drops. I could actually do a good measurement around them. So this is the one that I picked for the talk. So this is the sequence of the experiment. We filled the micromodel with oil and then used water to recover oil, looked for oil blobs, and then we found some. And then put tracer particles in water. Now just continuously go the same velocity, nothing should change, and measure velocity around this. And then do polymer flooding. Right after polymer flooding, put the water with tracers, drop the flow rate extremely low, because now I'm doing the chase water and I don't want to disturb the oil, and remeasure the velocity. Luckily, when it's very slow, you can just multiply by the factor you have reduced it. And then go do the chase water at the same flow rate that you started. And then take all the data and do a particle tracking and measure the velocity of tracer particles around it. So these are on different scales, and then I put them on the same scale. So the original image is high resolution. When we do particle tracking, we have bins, and then we have to put them, so they get a little off. But you can see that before we had, this is the oil. I colored it purple because now we can tell the difference between oil and glass bead. And these are water velocities. So we have this major highway. Most of the water is going through that. After polymer flooding, is still the major highway. The velocities is around like 1.5 times larger, but there are some differences in other places. So there were some places, and so I should explain that. In confocal, you can choose to have a 2-micron plane or a 10-micron plane, and when you don't have a lot of data, just open the pinhole, get a little more data. And then we have some that are out of plane, so there's something happening here. But in the same plane, we have this part that had barely any velocities. Now it has 8 times larger velocities. Now we have some data we can work with. Unfortunately, to do scans with confocal is very limited. So I did not have enough time to actually scan around this oil blob and get a full picture of the velocity. But with the 2D velocity, we can just use some first principles. We know what's the curvature of this oil blob, but the oil is in 3D, but the velocity is not. And then we know what's the interfacial tension. We measure capillary pressure. And then we know what's the velocity around this just by, we can measure the stress, and we know the area, just sum them up and measure what's the viscous pressure. And when we put these two numbers on the same page, we get very close. So before we started, before polymer flooding, this value for the viscous is around 60. And then after that is 140, capillary pressure is the same, so it's 280. We get very close for actually mobilizing the oil. And we could prove the observations based on bulk permeability and how much polymer is stuck in the medium based on other core flooding measurements. We have now direct evidence that there is redirection of the flow and it can mobilize the oil. And if you ask me what was the largest contribution I had on industry, was first of all, we provided an understanding and a possibility of a different mechanism. And also we told them let's use less polymer. So polyacrylamide, when it's broken down to a monomer, it's carcinogenic, and it's not good to have it around alcohol. So if we have less of it, that would be much better. And now the mechanism is different. Now they don't have to look for oil fields that the viscosity is low. They may be able to recover from viscous oil reservoirs. So I'm going to skip this. This was a side project that came out of it. And I'm going to talk about what I'm doing at this time at RIT. So we learned that in porous media, everything is heterogeneous. Things can couple throughout different pores. And this is what I'm doing at the RIT. So this is a 2D porous media. This is a regular lattice, and this is just a random lattice. So a 2D porous media is that you get a glass slide, and you have posts that are just like one cut of an actual rock. You put posts on top of it, and then put another glass slide. So the scale is, these are like 200 micron posts, and this is made of PDMS, so this is soft lithography. And I'm setting it up in the lab at this time. And I'm going to look at emulsion in porous media. So this drop was stuck in this porous media for a while, and then we were watching it for a few minutes, and then this one came in. And as soon as this one passed through, over one pore, the velocities are coupled. So this one started mobilizing this one. And then this would be more related to oil industry, where you have many drops. So this happens in a couple of places. One of the methods of increasing recovery is to put surfactants. So the surfactants are like dish soap. They decrease the interfacial tension, and then you create a small emulsion of oil in water. And now an emulsion has a higher viscosity, and then they go through and they usually recover more oil. And if we know a little more about how the dynamic is and which pores they cooperatively use and how they can push each other to different areas, the pores that are usually not used, we can learn a lot. And the part that we're going to do, and it took 2 years of summer students at Harvard to develop this for me, was to make exact monodisperse drops that you can do very precise measurement on them. When you have a lot of drops, that's a large volume, so it gets really hard. But when we can do very precise measurement, it's going to be a better contribution, considering that we are a research institute, not industry. And I have PhD position available if you want to talk to me at some point. I'm upstairs and downstairs in the lab. And I really like collaboration. I want to thank all the students and all the faculty who came, and I hope that we can continue collaboration. And I have to thank my awesome advisor, Professor Waits at Harvard, and the collaborators over the years that they all contributed a lot. And a lot of the work was actually done by the students. The students, they came from different backgrounds. Most of them visited us for a short time, less than a year, but they got a lot of things done. Especially in the projects, in the 2D projects, this is something that if someone wants to do a master project, it's a perfect problem because it's very simple to set up, and then you just need to be creative to get something out of it. Thank you.
Any question? We have a limited time, but we still can have a couple questions. Yes, Carl.
So percolation theory has been around for a long time. I guess this is part of that. Is that right?
Yes.
And it's kind of universal. So you mentioned resistivity, for example, and materials, et cetera. So what's kind of driving the frontiers of percolation kind of problems these days? Besides this industrial problem, what are the kind of problems that still need to address?
So Ariel, he is my collaborator, and this is all his business. So what he's been working on recently is neural network, and also Karen, who is now at Max Planck, she used this to exactly percolation theory to understand how how fluids are connected in roots, and how signaling is happening in roots. So that was one of the. I'm not sure if they are the frontiers, but they are problems that are still bugging people. And well, so for the images I showed that they were just velocities, we are using percolation theory to actually explain that how the distribution changes.
When you showed the velocity of the water moving through, you were showing the motion of, you said, tracer particles? So what were you actually tracking in there? So water was moving through, but...
So
yeah, in these images
yes.
here.
Yes.
So what are you, in the imaging systems here, what are you actually tracking frame to frame?
Tracer particles.
So what do you use for the tracer particles?
Okay, so these are our micron latex particles. We made them in the lab with a polymer brush on top of them, not to stick to the glass. And they excite us 514.
Okay, so these are fluorescent
Yes.
particles. I see. Okay.
Any other question? If there is no question, we have a reception outside, and if you want to discuss with Dr. Parsa, you have to feel free to have a discussion together during the reception. And as she has already mentioned, her office is in the second floor of this building. So it's easy, really easy to go upstairs to have a talk. Okay. Let's thank Dr. Parsa again.